find, we have that Kyung-yoon, I don't know if I'm saying that correctly, but Kyung-yoon investigates the rate at which a cubical block of sugar dissolves in hot coffee. Initially, the cube has side lengths. Okay, that's important. We're talking about side lengths of 10 millimeters. This information is illustrated in the following diagrams. So yes, it's a cube because it's just a bunch of squares lined up, ¿cierto? And all these different sides are all 10 millimeters. So Kyung-yoon predicts that as the block of sugar dissolves, each side length will decrease at a constant rate of 0.2 mm, and this is important, per second. And so for part AI, we need to find, according to this model, the length of one side of a block of sugar 20 seconds after it is placed in hot coffee. So it's specifically after 20 seconds how much, or how long I should say, the length of one of these sides ends up being, right? And so we know that it starts at 10 millimeters, right? So it starts at 10 and it loses, so we're going to put a minus, right? It loses a certain amount of those millimeters per second. How many millimeters per second does it lose? It loses 0.2 millimeters per second. So in that sense, we can put 0.2 mm. I mean, sorry, not mm. This is all in mm units, right? But technically, it has 10 mm, right? And it loses 0.2 mm per second. And so in order to express this per second right here, we're going to go ahead and put 0.2x, right? So my function f of x, all it's really doing is that x is going to be seconds. My x is going to be seconds, and my y, which is the same as f of x, see, is going to be my length, all right? And it checks out because if I am at, for example, at 0 seconds, and I plug in 0 for x, so x ends up being as 0. It makes sense because this 0.2 times 0 is just 0. F of 0 is 10. So it makes sense that at second 0, before I even put it inside of the coffee, it's still at 10 millimeters, right? So all I have to do now for part AI is simply plug in f of 20, because we are talking about after 20 seconds, okay? So f of 20 has to be 10 minus 0.2 times 20. And so f of 20 has to be, let's go ahead and confirm with our calculator over here, 10 minus 0.2 times 20 ends up giving me 6. Okay, so the length of one side of a block of sugar 20 seconds after it is placed in hot coffee will in fact be 6 millimeters. Okay, so that is for part AI. For part AI, we need to find the volume. So this is a little bit different. The volume of a block of sugar 20 seconds after it is placed in hot coffee. So what the heck is the volume of a block of sugar? Well, the first thing we need to immediately say out loud is that a block of sugar is the same as a cube. Okay, it's the same idea. Block of sugar, cube of sugar. Okay, and the word cube or block, is that in my formula booklet? I actually have no idea. But that's the point, ¿cierto? The day of the test, you're going to be walking in with a couple of things. A pen or pencil, an eraser, a calculator, 2 years of experience of this thing called IB, 2 hours of sleep, and the formula booklet. Guys, the formula booklet, you do not have to know it by memory, but you should know sort of what's inside of it. See? So the moment you read cube or block and volume, you should be thinking, there's a whole section in my formula booklet that has volumes, right? Let's see if it's in here. See? And lo and behold, I immediately see volume of a cuboid. Okay, so volume of a cuboid, volume of a cube, is simply going to be length times width times height, where L is the length, W is the width, and H is the height. And so over here for part AI, well, what would be the length? Or actually, let me write the equation. See, so for part AI, the volume is going to be length times width times height. And we're talking about after 20 seconds, see? So after 20 seconds, the length of one side of a block of sugar after 20 seconds, how much did it end up being? It ended up being 6 millimeters, right? And so this cube that used to be 10 per side is now a cube that looks something like this. See? So now instead of being 10, 10, 10, 10, 10, now it's going to be 6, 6, and 6. Okay? So that means that length times width times height in this case is going to be 6 times 6 times 6. And that ends up being, let's find out, 216. Okay, so for part A double I, what we end up finding is that you do 6 cubed, 6 times 6 times 6. It gives you 216. The units are millimeters, so mm cubed. I'm going to go ahead and put it in blue so that we remember that that's the answer. And there it is. ¿Vale? So that would be for part A double I. Then they tell us that we need to let the function v of t represent the volume of the block of sugar, millimeters cubed, t seconds after it is placed in hot coffee. And that Vt is given by this equation there. Okay, now let's go piece by piece. On the one hand, this is my equation, right? And on the other hand, the thing that I'm putting now in yellow, the t being between 0 and 50, all this is really telling you, or what it's defining you, is your domain. Okay, this is a classic. Sometimes they give the domain, sometimes they give the range. And all the domain really tells you is your possible values for x. Okay, and in this context, like your x, cierto, your independent variable in this context, clearly has to be time because it's in here, cierto? F of x, here you have v of t, so x is time, while your y is going to be volume. Okay, so all we know is that this model right here for volume of a block of sugar in respect to t seconds after entering a hot coffee, blah, 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 blah. All we know is that this model is useful, or we're going to consider it, for between 0 and 50 seconds. Okay, we can't use above 50. All right, and so for part B, you need to find whatever this is. This, ladies and gentlemen, the weird stuff that they can throw at you are 3 things. Okay, or well, not weird things, but the functions that they can throw at you. You can have f of x, which is like it's the normal one. Okay, this is the normal one. Okay, then you can have this, which will be the derivative. Okay, the derivative. And then you can have this. And that with the -1, cierto? This isn't a 1, this is like an asterisk thing, much like that symbol here. And f to the power of -1 is actually going to be the inverse. Okay, these are the 3 sort of functions that at AISL they can throw at you. In this context, I need you to identify this symbol as a derivative, cierto? So, derivatives. Probably not too exciting. You probably didn't understand it in class, and that is why you're watching this video. So, what I need you to do when you face a derivative problem at the AISL level is that the moment you see it, you're going to take out your formula booklet, you're going to listen to this guy online talking about math, and you're going to scroll all the way down until you reach the calculus section, topic 5. And over here, the only derivative that we need to know for AISL is this derivative here, the derivative of the exponent. I do have a video explaining this a little bit more. I think it's called like derivative of an exponent 101 or something like that, but I'm still going to give you the rundown on how it works. See? What I really need you to focus on is what happens to your exponent, what happens to n, cierto? So this right here, the x to the power of n, is before the derivative, and this with the derivative symbol is, well, after the derivative. So what happens to n? 2 things, okay? 2 things. On the one hand, you're going to do -1 to the exponent, okay? And the other thing you're going to do is that you're going to sort of like multiply the exponent below, okay? Because notice right here, the n dropped from above multiplying, so that's number 2. And we also did a -1 to the exponent, so that's number 1. See? Okay, one thing is looking at it here on the formula, okay? And you can sort of figure out what it does by really focusing on what is happening to n. But really, for me at least, learning the derivative of an exponent, it helped me a lot more to see examples. So let me give you like 2 or 3. See? You can have the example of x squared, which if you do the derivative, you end up with 2x, because this 2 is going to multiply in front, and then 2 minus 1, because you got to do -1 to the exponent, ¿cierto? So that ends up as 2x to the power of 1, which is the same as just leaving it as 2x. Let's do another example. Let's say you have x to the power of 3. That means you end up with 3x to the power of 3 minus 1 equals 3x squared. And the last example I'm going to give you is actually 2 more. See? Imagine we have 2 times x to the power of 4. So that means I end up with 2 times 4 times x to the power of 4 minus 1. So that means I end up with 8x to the power of 3. And the last example I'm going to give you, which is kind of wild, it doesn't usually happen, but if you do run into it, it can be something like, I don't know, 1/2 x to the power of 3. See? So in this case, you end up with 1/2 times 3 times x to the power of 3 minus 1. So that means you end up with 3/2 x squared. See? So that one's a little bit crazier because you're working with a fraction. Oh, and the last thing I'm going to show you now that I'm, talking about this, whatever, let's just jump into it. Who cares? You can skip ahead if you already know it. But you can encounter something like 1 divided by x. See? So if you need to do the derivative of this, 1 divided by x, all you need to do is like before the derivative, ¿cierto? So before the derivative, so this is before derivative, okay? It's very important that we understand that this is before derivative. Before the derivative, what you can do is put this x on top, right? And in order to put it on top, all you need to do is put x to the power of -1. Let's remember that anything that has a negative exponent, you kind of like flip it, see? So x to the power of -2 ends up as 1 divided by x squared. 3x to the power of -3 ends up as 3 divided by x to the power of 3, okay? And so before the derivative, you're going to flip it, and then you do the derivative. And so if from here you do the derivative, you end up with -x to the power of -1 minus 1, which effectively gives you -x to the power of -2. And if you want to write it more nicely, you end up with -1 divided by x squared, okay? So I pretty much showed you everything you need to know for the derivative of an exponent. So from here, it should be fairly easy to do. All right, coming back to reality, for part B, you need to find the derivative of this whole thing, and we gotta go piece by piece, see? So if I do the derivative, actually, yeah, let me write it here. See, so v of t is 1000 minus 60t plus 1.2t squared minus 0.008 t to the power of 3, right? So if you go ahead and do the derivative from here, okay, if you do the derivative from here, it's very interesting to what happens with this first term, right? Because as we saw in the formula booklet, the derivative of an exponent, like the exponent goes down multiplying, ¿cierto? And it has an x next to it, right? It has an x next to it. So what do you do when there isn't an x next to it? Well, technically, it does have an x next to it, see? And this is going to be kind of crazy, but technically right here, notice how all of these are being multiplied by t, ¿cierto? T to the power of 1, t squared, t to the power of 3. Technically, this 1000 is also being multiplied by a t, just that this t is to the power of 0, because anything to the power of 0 is going to equal 1, and 1000 times 1 doesn't change your outcome, see? So, point is, technically there's a t to the power of 0 there, ¿cierto? And so if there's a t to the power of 0 right there, then that means that for this first term, we end up with 1000 times 0, ¿cierto? Because the exponent multiplied right in front, times t to the power of 0 minus 1. For this next term, we end up with minus 60 times 1 times t to the power of 1 minus 1, because this is to the power of 1, ¿cierto? For this next term, we end up with plus 1.2 times 2 times t to the power of 2 minus 1. And for this last term, we end up with 0.008 times 3, because this 3 is now multiplying in front, times t to the power of 3 minus 1. See? Now all these minus 1 solve pretty easily. This first term is being multiplied by a 0, so all of it ends up being 0. And what you end up with at the end of the day, well, this first term is 0, the next term ends up being just negative 60 times 1. This 1 minus 1 gives you t to the power of 0, which is just 1. So this is multiplying by 1. See, we don't really care about that. All I really end up with is minus 60. ¿Vale? So this next term is going to be minus 60. This term here, so this ends up minus 60. This ends up being 1.2 times 2, so 2.4 times t, so plus 2.4 times t. And for this last term, you end up with 0.008 times 3, so that should be minus 0.024 times t to the power of 2. Okay, and just so that you believe me, we are talking about number 9. And well, there's the 6, there's the 216 that I mentioned earlier, all good. And for part B, there it is, the negative 60 plus the 2.4 minus the 0.024. So that would be for part B. Okay, and now for part C, we need to find the rate of change of the volume of the block of sugar at t equals 20. This is extremely easy, but you need to understand how derivatives work. See, so you need to find the rate of change. Find the rate of change when t equals 20. Now I need you to understand this very key concept, ¿cierto? When we're dealing with like the original, when it's f of x, right? Think about it this way. If you plug in an x, you're gonna get a y, okay? And let's say you plug in x of 1, you get a y of 2. That means you end up with that set of points 1, 2. Makes sense, right? If you have the derivative, okay, and you have an x and a y, and you plug in, I don't know, x of 3, and end up with a y of 7, then yes, this is also technically 3, 7, but the interpretation for the derivative is a little bit different, okay? For the original one, you have like, you get like a set of points, so 1, 2, if x is 1, y is 2, blah, blah, blah. There's not, I mean, depending on the context, it can give you something, but the derivative, the interesting thing about it is that now your y has turned into rate of change. So in this imaginary example that I gave up, when x equals 3, slope equals 7. Slope is the same as rate of change, okay? So the slope equals 7 when x equals 3. And that is the information that the derivative gives you. And you can also work backwards, by the way. If you go ahead and plug in, I don't know, a y of 0, and you discover an x of 2, then that means, and this is very useful for parabolas, okay? That means that right when x equals 2, you have a slope of 0. And wherever you have a slope of 0, always has to be a maximum or a minimum. See? So I'm just telling you, this is what derivatives are for. That's usually what it's used for. A lot of times you equal your derivative to 0 because you're asking the function when the slope is 0, what is x? And that can be extremely useful for finding maximums or minimums, optimum points, stuff like that. So back to reality once again. These monologues where I teach random stuff, well, I'm sure it's useful, but videos end up being a little bit longer. So for part C, you need to find the rate of change of the volume of the block of sugar at t equals 20. So technically what you're doing is you're going to plug in 20 for x and find whatever your y is. How come you plug it in for the derivative and not for the original one? Because the original one in this context, you give t, you get volume, ¿cierto? You give t as time, you get y as volume. And now with the derivative version, yes, x is still time, but now y is slope or rate of change. ¿Cierto? Same thing. So now your x is still as time, but your y is now a slope. And so they're telling you that the t is 20, your x is 20, and what is the slope? Right? That is what you're dealing with. what is the slope when x is 20? And so of course I gotta use the derivative version that I have right here. So if you go ahead and plug in 20 into that, you end up with negative 60 plus 2.4 times 20 minus 0.024 times 20 squared. So if I put all of that into my calculator, we end up with negative 60 plus 2.4 times 20 minus 0.024 times 20, and that guy squared. See? Go ahead and press enter. You end up with you end up with negative 21.6. Yeah, negative 21.6. And if we go ahead and check the answer key, there it is, right? Now, because this context is within volume, ¿cierto? You end up with a very weird sort of unit. Because we're talking about rate or slope or whatever, then we're talking about, oh, you're losing at 20 seconds, ¿cierto? At 20 seconds, you're losing 21.6 like cubic units of millimeter per second, ¿cierto? And that's why over here they express it like that, ¿cierto? Remember how I mentioned earlier that anything to the power of 1, you just flip it? Well, saying mm cubed times s to the power of negative 1 is the same as saying mm cubed slash s, which is what we're used to seeing, because mm cubed slash s is the same as mm cubed divided by s. See? These are all the same. Now maybe you understand the negative 1 a little bit more. See? Yeah. Enough blah blah. That was for part C. And the last blah blah that you have to go through is part D, which says, fairly easy, state one reason why the side length of the cube may not always decrease at a constant rate. And this is interesting for two reasons. First of all, because it's a classic question, it's like a reasoning context sort of problem. But secondly, because it allows me to tell you, dude, if the day of the test you're scratching for points, ¿cierto? You're trying to get as many points as possible, and there's a couple questions that you left unanswered because you weren't sure about them, or you were running out of time or something like that. Try to be on the lookout for these sort of like context questions, okay? Because these context questions, although they tend to be only worth 1 point, you need to realize that you do not need part A, you do not need part B, and you do not need part C in order to answer these context questions. So if you're running low on time and you want to get a couple extra points, be on the lookout for context questions so you can answer them quickly, or maybe even answer them right away. You know, why not? Who cares, ¿cierto? But yeah, so in this context, we need to state one reason why the side length of the cube may not always decrease at a constant rate. And let's first understand that when they say a constant rate, it's like a number that, like, how do I say it? It's always the same, ¿cierto? Imagine I tell you my height, ¿cierto? So since I was 1 year old until I was, 18 years old, my height always increased every year by 10 centimeters. And that's not true, right? When I was a baby, I was very small for quite a while. And then when I was a teenager, I grew a lot in very little time. It wasn't always 10 centimeters per year, right? And the same sort of reflection can happen within this context, right? Why would the length of a cube may not always be a constant rate? One of the reasons that comes to my mind is, for example, I imagine that the smaller it is, the faster it sort of fades away, or the faster it decreases its volume, because the whole shape is like a little bit weaker, right? You can also say like the cube the first second is not so hot, and after 20 seconds it's very hot, so it's gonna decrease faster. There's a lot of things you can say here, guys, okay? Just go with one of them and make sure you answer as completely as possible. I think for these questions, it's better if I show you the answer key so you understand the sort of stuff you can say. But over here, the answers that they accept, not only is any reasonable explanation, but also they give some examples. So decreasing or changing coffee temperature, the temperature of the coffee is also changing, right? Decreasing or changing surface area of the cube, that's what I meant about the cube getting smaller, right? The cube breaks apart into smaller pieces. I did not consider that, but it's a little bit related to the second one, right? And the dissolution rate rate related to the volume of the cube. That's very much related to the second thing I said. See? So again, for these exercises, for the context problems, for the context part of the problem, there's a lot of different stuff you can say. Just trust your gut, think about it logically. You only have to give one. Okay, you only have to give one. It's 1 point. Don't stress over it. This should be a quick and easy sort of question. Trust your gut. That it? Ladies and gentlemen, that would be for number 9, and I hope I helped. If there's something I can say about these sort of exercises, is that finding the derivative at the AISL level is very easy. Take your time to learn it, because for me at least, it's very easy, 4 points. And I'm just saying, there's usually at least 1 or 2 questions with derivative within the IB exam for AISL. So worth looking into it. It's worth studying. You should get those points pretty quick, ¿cierto? And if we consider like the amount of time you spend on a question and how much points it gives you, for me, derivatives tends to be the better one in that sense. Like, usually they say like, oh, you spend a minute per point. I don't think you end up spending 4 minutes with the derivative and the rate of change and all that stuff. See, derivatives are pretty quick. This video is longer because I'm explaining a lot of stuff, but you should reach the level where doing the derivatives that I drew, for example, over here, should be very, very easy for you and very, very quick. Okay? Eventually, maybe you even skip the step of like writing out the in-between step, and you effectively go from here to here more easily. See? Point is, derivatives are worth looking into. They show up a lot in the tests, and that's just an additional tip I wanted to give you for the day of the exam. So now, for sure, I hope I helped. I'll see you around, and take it easy.